What is up, gamers? Welcome back to another very exciting video. It's gas time. We're continuing gases. We're talking ideal gases for now. Most of us finished page 17, I believe, but here's page 17. Ask someone to pause it if you need to take a look at this, or if you need any clarifications on these values, but hopefully that's a pretty straightforward problem. We're going to be looking at some more complex problems on page 18 for a sec. So find page 18, looks like this. Yeah. So you've already done your homework, so I believe you've already had a kind of situation like this. So let's talk through it together. Some of us might already feel kind of confident. Maybe we were completely confused, and this will help give some context to that homework problem, but time will tell. Okay. Let's get ourselves oriented. The figure, for some reason, being capitalized. We have two sealed containers. So we have two different 2-liter boxes, one containing argon, one containing xenon. We are told the initial pressure of argon, but we are not told the initial pressure of xenon. Both gases are transferred into a new container that is 1 liter, and it's asking about the new total pressure. That is what is being implied here. So, it's kind of hard to tell where to start on a lot of these. So let's think about the goal. I like to start there personally. So I want to know the pressure in my new container. And I know that there are 2 different gases in my new container. So I know that if I want to figure out that new pressure, I'm going to have to consider the partial pressure of my argon, and I'm going to have to add that with the partial pressure of my xenon. And I guess for clarity, we need to figure out my final pressures on both of these because they both have an initial pressure and then a change occurred, and we're going to have to figure out like what that change has done to our pressures. Okay? Let's talk about the change first. I don't know. I like doing that. Let's look back at this problem. And we want to think about each gas kind of individually. What has changed about their situation? And then we can think further about what happened to their pressures. So, what changed? From argon's perspective, it had a 2-liter box, and now it has a 1-liter box, right? Same for xenon. It went from a 2-liter box to a 1-liter box. So that is the change that has occurred. We don't have to worry about interactions. We don't have to worry about size. We don't have to worry about anything except for the impact of that variable because it's not ideal gas. So, what is doing this to pressure doing this to volume due to our pressure? Hopefully, you could figure that out. So again, the change, and this is for both gases, so I'll just put a little note off to here. They both have half the volume. So hopefully you guys could determine, okay, well, if my volume went down by half, that must be accommodated by my pressure being twice as large as it was originally. So my formula, I could rewrite it. My final pressures are going to be 2x my initial pressures. I guess I'll use initial. Okay. Again, I'm choosing to do it in this order. You could solve it lots of ways. Okay, but I still need to know my initial pressures to figure out what my final pressures are. So let's think about that. Let's reread the problem. Think about what we can determine here. Hopefully argon's straightforward, right? We just know from the problem that the initial pressure of argon was 2 atmospheres. 2.0, I suppose. Yay, sig figs. Okay, but I don't know, they didn't give me the initial pressure of xenon. So I kind of have to think again and put on the cap and try to figure out this initial pressure going on with xenon. So, yeah, talk to a neighbor real quick. Pause briefly, I don't know. And hopefully, given enough time, comparing these 2 boxes. Again, these are ideal gases, so it doesn't really matter. It does not matter what gas it is. It doesn't matter any of the specific things about the type of gas. But looking at these boxes, my volumes are the same, but I notice that this one has 6 moles of gas, and this one only has 3 moles of gas. And I know that if there's half the amount of gas, half the amount of moles in the same spot, I know that because of my equation, just to be clear. If I have half the amount of moles, everything else constant, I must have half the pressure to maintain this relationship. So if I have half this versus this is half the amount of moles, so it will also be half the amount of pressure. My initial pressure of xenon is 1 atm. Awesome. So a little bit of thinking off to the side. My initial pressure of xenon is 1 atm. And finally, now that we put all our pieces together, we can actually do some solving. So I have 4 atm and 2 atm. Sorry, I keep forgetting my point O. Hopefully we can all see that that is a total of 6 atm in my new small box. Hopefully makes sense. Little logic check, way bigger than it was earlier because we saw the volume decrease and now we have 2 partial pressures. So that tracks for me, and that is how I would go about solving that problem. So again, always the hardest part of it become how do you actually start the problem? But hopefully that helped orient you and maybe helped clarify some of the homework. I believe you had to do 1 or 2 of those. Okay, look at 4 and 5. Pause the video, try it with your neighbors, go. And you definitely did that, and now we understand things, and let's talk. All right, so we have 2 containers at the same temperature. One of the containers, the same temperature, the same pressure. Sorry. We have 2 containers, same volume in both, same temperature in both, but I'm wondering about the pressure because I've changed the composition of my box. So how would that affect the pressure? And hopefully you told your neighbors it wouldn't, because there's nothing in the ideal gas law related to identity. So as long as I have the same amount of total moles of gas, which it looks like I do, and I have the same size box and I have the same temperature box, then the pressure should be the exact same as in the other container. Okay? Nothing about identity in my ideal gas law. How about this one? I took a piston and I squished my gas and now its volume is way smaller. How is that going to affect the motion of those particles? And hopefully you said, you didn't catch me, Miss Mullen, because I know that, of course, if temperature is constant, the definition of temperature is that is the only thing that affects kinetic energy. So hopefully you caught that this would have 0 effect on kinetic energy, because only temperature has an effect on kinetic energy. This change in volume would only affect the pressure, not the temperature, not the kinetic energy. Hopefully that wasn't too hard, just tricky. Cool. I don't know why I chose to put these here, but here are a bunch of gas-related terms. Vocab stuff that I just want you to hear from me before you see it in problems and just around and be confused by it. So, one thing is called STP, standard temperature and pressure. Just a thing we use sometimes. A lot of the time you might see a situation where it's like, oh, you have a gas at STP. What the heck does that mean? This is on the equation sheet because the College Board is sometimes generous. Standard temperature and pressure, we're talking about like, I'm at sea level at a reasonable room temperature, which we define as 1 atmosphere, 1 atm, and 253 Kelvin. I don't know why I said it was a room temperature. That's 0 degrees Celsius, just to clarify. But I don't know. That's what we chose as standard temperature and pressure. A cool derivation of that, you could do the math if you feel like it. This is also on the equation sheet. I will point out if you have an ideal gas at STP, you could, of course, solve for volume by plugging stuff into the ideal gas law, blah, blah, blah. But if you want to save yourself a little bit of time and have a value you could potentially use in stoichiometry, because that is your favorite type of calculation, any gas that is at STP will have a volume of 22.4 liters per mole of gas. So if you have that in your back pocket, remember it's on your equation sheet. You can save yourself a little bit of time on your calculations. And how fun is that? The term atmospheric pressure refers to the pressure from the atmosphere. So how much pressure is exerted by all of the gases above me onto the surface of the Earth. We're assuming at sea level, unless told otherwise. So that means 1 atm, usually. If they don't tell you, you assume it's STP. The term barometer, baro means pressure. So barometer is the tool we use to measure pressure. So if you ever hear that term, that's all they're saying. They're probably about to give you a number to represent pressure. There's all kinds. I don't think it's worth going into like how they work for the sake of this class. Just if you see the term, know that's what it's for. Inert gas. Inert means unreactive. Reactive. Okay, so if we're having a problem where all we're like trying to talk about is pressure and temperature and volume and all these variables, I don't want any reactions to be going on. I just want to think about the pressure or whatever. So very common for us to say it's an inert gas. We kind of assume if it's an ideal gas, it's inert. I bet I could ask you if I was there, which types of elements do you suppose are usually the inert gases? And hopefully you all would say, oh, noble gases are the ones that don't react. So often the case, like if you want to think of it as, oh, there's noble gas in the box, that works. They might not always specify that, but just an unreactive gas is what we mean by inert. Equimolar, so equal molar. So if you see that means there's equal amounts of both of the things in the mixture, equal moles. Cool. If you hear the term evacuated, often they'll say like, you added this much gas to an evacuated container. Evacuated means they have already like vacuumed out all the other gases. So a totally empty container. Okay, and finally, a fusion, that is specifically referring to, it's the same as diffusion, but we're specifically talking about a gas, so a gas that is able to go through a barrier. Yesterday we discussed this in context of like when a balloon deflates on its own, it's because the gas is banging against the walls and eventually effusing through the balloon walls, and the amount of gas actually contained decreases over time because of that. Okay? If you can think of more vocab things that have come up with this that you don't know what they mean, I don't know, write them down, email me, and maybe we can add to this list. But hopefully this will make navigating some of these word problems a little bit more clear. Okay, cool. So, ideal gas. How wonderful. How beautiful. Piv nerd. Of course, not real. We do ideal gas a lot of the time, but we also have to understand, okay, well, when is that completely unrealistic? What are the consequences of real gas behavior? How does ideal gas assumptions fall apart? KMT assumptions fall apart. So let's discuss. Reminder, again, these are the really important postulates, the really important things that we assume as part of KMT, as part of saying something is an ideal gas. We assume they don't interact with each other. No elastic collisions, no sticking, no repelling. And we also assume that our volume of the gas is negligible. We assume that like the size of the particles does not affect its behavior at all. So what is really going on? Like, what are some things we actually expect? So let's consider one at a time, shall we? Particle interactions. We ignore these. We pretend they don't exist in ideal, but if they are happening in a real situation, what consequences does that have? What data might we observe? Just to emphasize, when I say particle interactions, we mean IMFs, like sticking together, non-elastic collisions because they want to interact. Just to clarify, that's what we are thinking about when we are talking about this. So let's check it out. This box is representing my ideal gas, while this box is meant to be representing my real gas. Okay? So you can see in the ideal one, they're whizzing around, they're doing their own thing. Awesome. And the real gas, we are seeing, it's trying to illustrate that those particles are actually sticking together, interacting as they're whizzing around the box. Okay? So let's think about what that does. Cool. The data you would expect to see if this was occurring, and you can kind of, look at the pictures, imagine it, is a difference in pressure. So in the ideal situation, my particles are bouncing around the box, hitting the walls of the container with a certain frequency, right, with their mass. In this situation, when we have our real gas, you can imagine if I'm sticking with my neighbors, if I'm doing my IMFs, I am hitting my walls less frequently. Can you kind of imagine that? Like in this one, instead of having two separate collisions of this mass hitting the walls, instead there's just one collision because they are interacting momentarily while they're in the box. So we observe that the pressure is less than expected. If you have a molecule where those IMFs are really strong, where they're very likely to actually want to interact and stay together, very likely to want to condense, very likely to want to be with their buddies and become a liquid instead of being a gas. If we see that, then as shown in the picture, what we observe is that the pressure that is actually recorded by the real gas is less than that expected of my ideal gas behavior. Okay, so know that IMFs can mess up ideal behavior. Know that that means less collisions, aka less pressure happening in my box than I would expect. I will point out, this is less of an issue at high temperatures. So you might want to, think about that as an exercise. Make sure you can talk this through to yourself. Why do we see a lower pressure? Why would high temp make this not as much of an issue? Again, these are IMFs. So at higher temperatures, for one, those interactions are more likely to be broken. It's more likely to be in the gas phase than being tempted to be into the liquid stick together phase. Also, if I'm moving faster, because my kinetic energy is related to my temperature, if I'm moving around the box faster, there's less opportunity for me to just stick to my buddies and have this effect. So something I'll point out there. So this is more of an issue at low temperatures, conversely. All right. The other huge assumption we made, molecules don't take up any space. Why would they? But in reality, of course, they do. So again, let's think about what this would do. So this one, again, is my ideal gas in this box, while my realistic gas is over here. So let's look at this. Same volume. No. Same volume box. Same amount of particles in the box. But now you can see my real gas actually does have a significant volume. So let's think about what the consequences of that are. As it says down here, well, now my particles are taking up more space. Can you talk through and rationalize to yourself? It is more likely to hit the walls because now it's taking up more space and like gonna be hitting the walls more often just because there's less in between space now. Can you see me on that? So in this case, you're seeing more collisions. So the opposite expected result of the IMFs, if there's a significant size and that's what's messing with ideal behavior, instead we're going to see our actual pressure be greater than our ideal, as said there. I think I misspoke up here. Or another way of thinking about this one, I guess. Sorry, I'm trying to decide if I like already explained this well enough. Whatever, I'll say it again. They're kind of taking up less space in a way. Like, if they're sticking together, like, I think I already said, like, there's less opportunity for collisions with the wall if they are sticking together and wanting to condense instead of being gas-like and colliding with the walls. Yeah, I feel like I just made that more confusing. It's fine. I will also point out with this one, this is less likely to be an issue if you have a big volume. Right? Like, if the box is so huge that by comparison that difference in size is negligible again, then it's unlikely that that size of molecule is actually going to affect the frequency of collisions. Also not as much of an issue at low pressures. Again, just if not very many strong collisions are happening, then like the frequency of them has not as big of an effect. These are all very interconnected. Of course, all these properties affect each other. So in summary, there's kind of 4 different ways, depending on what the question you're given is. You just kind of have to know like what is ideal behavior, or when is ideal behavior likely, when is non-ideal behavior likely. I paid for this meeting. This is not a freebie. Oh, it's fine. It's fine. We're moving. We're keeping pushing. Anyway, so let's summarize those, shall we? Before I apparently get cut off. Low temperature. Right? And then high pressure. As mentioned, just you need this in your brain. Non-ideal behavior at low temperatures, not moving very fast, sticking together, hanging out, condensing even maybe. High pressures, they're all in a, lots of collisions, lots of restricted space, essentially. Cool. And as we illustrated, significant IMFs could kind of overcome our assumption about IMFs not mattering, and significant size. Cool. How exciting. Pause and try the next 2. And let's pretend you did that. Which of the following would be least ideal? So I'm at a pressure of 1 atm and I'm at a temperature of 300 Kelvin. So those are reasonable temperatures and pressures, right? This is not an extreme situation. So I'm going to think that this is not really because of the temperature or the pressure. It's going to be because of something about the identity of these. So hopefully we went with that one because it has significant IMFs. It has hydrogen bonding capabilities. Or I'll just say strongest. Nope. Strongest. IMFs. Right? These are all fairly similarly sized molecules. I don't know, like, they're differences, of course, but like, if we got H bonds there, that's pretty solid. They're going to want to hang out. I'll leave it at that. And then here, you're just looking for that combination of temperature and pressure that we discussed. What is the most ideal? We want a high temperature and a low pressure, so I would go with B. That gives me the combination of those. So I'm going to pause this recording and deal with whatever is going on with my computer. There will likely be a second video. So whoever is operating this, go find the second video and then we'll continue on, because I feel a little bit cruel and this was not enough time to take up your wonderful lecture time. So I'll cut this one here. Happy gas calculating, and yeah. I don't know how to operate my computer apparently. Jesus. Sorry.